We're going to be talking about potential difference and batteries first. Now let's talk about these charges. If you've got two charges, you have something called an electric field. What would happen if you were to put a positive test charge in the middle? So what would happen to this positive test charge? It will be repelled by this positive charge and it will be attracted to the negative. So it would go to the right. So that is the direction of the electric field. That's how you remember it. You need a positive test charge so you will have an electric field. If you have two separate charges, it will have an electric field. What does this have to do with batteries? Now, a battery has a positive and a negative terminal. Let's just talk a bit here for a moment. So let's just say you've got two positives and two negatives. So for example, this could be 2 volts. The more negative charges on the right hand side, and the more negative on the right and the more positive on the left, the voltage will increase. So if you have 3 positive and 3 negatives, that could be 3 volts, for example, because you are separating a large amount of charge on either side. So you have 3 volts here, for example. In a battery, so this is a battery, you have an electric field. So an electric field that could be the electric field. Now the point is that at the moment it's not doing anything, because although you have a chemical reaction taking place, so inside there's a chemical reaction, however there's also a barrier in the middle here. So therefore, because there's a chemical reaction taking place, you've got oxidation and you've got reduction. Let me write this down. So in the battery, you've got reduction, you've got oxidation. It's a cycle. So electrons are being lost and gained inside this battery. However, there's also a barrier in the middle. Now, the electric field is waiting for the wire to come along. So what happens now when you add a wire? So let's just see what happens when you add a wire. So now you have a wire. So when you have a wire now, what's inside this metallic wire? The charges. What do we call the charges? So it's delocalized, isn't it? So you have delocalized electrons. Delocalized electrons, it's free. So the delocalized is free. If you have an electric field, and you've got some charges inside, the electric field can make the electrons move. So that's basically a current. So the electric field inside this battery is making the electrons move inside the wire. So that is a potential difference. So the potential difference is voltage. It's measured in volts. So the potential difference is measured in volts, is like a voltage, and is actually an electric field that makes the electron move. So the electric field, it makes the delocalized electrons move, which is another word, free to move. So the electric field makes the delocalized electrons to move around the wire. All right, now let's look at the positive and negative terminals. Now the one with the positive terminal has a higher higher electric potential, and the one that's negative has a lower electric potential. Just remember, the one that's positive is more and the one that's negative has less. So the positive has a higher electric potential and the one that has a negative has a lower electric potential. Now, what is the equation for energy, charge, and voltage? So the definition for voltage is energy divided by charge. So V is for voltage, that's voltage. E is energy, and Q is for charge. That is the equation for voltage. So voltage is energy per charge. Parallel and series circuits. Okay, so here you've got series and one you've got parallel. All right, so you've got a series. So here you've got two bulbs in series for the series, and for the parallel, you've got two bulbs in parallel. Let's just write down what we... Now for this circuit, there's only one loop. For this one, there are two loops. Now the current is the same throughout this circuit. The current is the same in this circuit. So if you have a current one here, and you've got a current here, and you've got current there, they are all the same because you've got electrons flowing in one road. So let's just say that you've got 10 cars in this road. So you've got 10 cars. The 10 cars. So 10 cars in this road, or it's more like a roundabout, isn't it? In the roundabout. So in this case, the cars represents the current. So if there are 10 cars, there's going to be 10 cars here in the whole circuit. There could be, so at this point, there could be, I mean, there's still going to be 10 cars. So the cars represents the charge that's flowing in this. So at this point here, there is still 10 cars in this roundabout. Here, there's going to be 10 cars in this roundabout. So if you write in symbols, I1 is equal to I2 equals to I3. Now, what about the voltage? Now, the voltage is a lot different. Now, the voltage is going to be in parallel. So here you'll be connected in parallel to this, and here is connected parallel to this. And here you've got the voltage across the battery. So the battery voltage. Now let's just say the battery is V3. So V1 plus V2 must be equal to V3. So all the energies that's used up in this circuit must be equal to the energy supplied by the battery. It's all about conservation of energy because energy is neither destroyed or created. So in this case, the battery supplied by the circuit must be the same as the energy lost by this bulb add energy lost by this bulb. So if you were to add these two voltages, you end up with the same voltage of this battery. All right, now let's talk about a parallel circuit. Let's call this I1 and this is I5. Let's call this I2. This is I3 That's why, okay, I4. So you've got I1, I2, I3, I4. Now again, let's just say that there are 10 cars. So the 10 cars in this what do you call it? In these two roundabouts. All you know is that there's a total of 10 cars. So if you were at this point, you're not sure if there are 10 cars in here, because that's one loop. Because you could have 2 cars there and 8 cars in this loop. So the cars represent the current. So let's just say you've got 10 cars, right? You've got 10 cars. You've got 10 cars all together in this diagram. But there are 2 roundabouts. So this is one roundabout and here's another roundabout. So there are 2 loops in this case. If you have 2 cars here, let's just say these are cars, you could have 8 cars in this roundabout. So what I'm saying is that here there's one roundabout and here's another roundabout. So if there are 2 cars there, there could be 8, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So there could be 2 cars there, and there's 2 cars there, and there's 8 there. So you don't really know. However, what you do know is that when you add these 2 roundabouts, you end up with 10. So the current is not necessarily the same, but what we do know is that I1 is equal to I2 plus I3 at any time. And you know that I1 must be equal to I4. Because this is what's common in both of them. That is common in both of them. So that's why when the cars join up at this point, it's always going to be the same as any one of those two circuits. In this case, the current is the same in the whole circuit. In this case, the current can be split up. Now, what about the voltage? Now, because you've got 2 loops, so here you've got a separate loop and here you've got another loop. So the voltage across each of these bulbs is the same. So let's just say here is 9 volts. Across here, you've got 9 volts. Across here, so let's just say this is V1 and this is V2, this is V2. V1 is equal to 9, V2 is equal to 9, because you've got 2 loops. So each of those 2 loops will have the same energy as the 9 volts.